we're going to talk about central limit theorem. Explains why we sample, why a sample is the only feasible way to study a population. Sample methods that we have. So on the test I might ask you about a sample method or why we sample, or give me an example of a sample out of this population. Design and construct a sampling distribution of the sample mean. Explain central limit theorem. And use central limit theorem to find probabilities of selecting possible sample means from a specified population. So we sample populations for several reasons. So you think about trying to do a study and take a sample would be a lot easier than taking a census. Doing a census every time you want to study something would be near impossible. And a census is like what they do every 10 years. The U.S. Census, they count everybody. They don't do a sample. So it would be time consuming, be very costly, and physically impossible to check everybody. If I wanted to take a sample, if I wanted to do a study on college freshmen sleeping habits, it would be physically impossible for me to go find and survey every single college freshman. And its destructive nature of some tests, sometimes when you interfere with the population, it can be destructive to the population, to those involved in it. So you take a sample of those and manipulate the scenarios to test things. And sample results are usually adequate if they're reflective of their population. So use this example at the beginning of the semester that we're going to study the college campus. I just wouldn't come here and ask business students because they're business students. They're most likely juniors and seniors. I want to make sure I have freshmen, sophomore, junior, senior, graduate, fraternities, sororities, athletics, whatever it is. I want to make sure I have an even mix of everybody and that the percentages are near the same. So if 10% of the students on campus are sophomores, I want to make sure that about 10% of my sample are also sophomores. Probability sample is a sample selected such that the item or person being selected in the population has an equal likelihood of being included in that sample. So students at Texas A&M Commerce, if that was the population, then anybody on campus or anybody enrolled would have an equal shot at being a part of my study. And it's my responsibility as the researcher to ensure that everybody has that equal chance. Some ways that we study probability sampling methods. We have simple random sample, systematic, stratified, and cluster. So simple random sample selected so that each item or person in the population has the same likelihood of being included. I put everybody's name in a hat, I draw 5 names, that's my sample. There's no organization. I may have all 5 of those men, which would not be reflective of my population. So there are issues with this. And here's an example, 845 employees, 52 were selected at random. Everybody has a chance of being selected because they put their names in a box and then they mix them thoroughly and then draw them out. And this is an example of just all the different combinations. And this is in random numbers and Appendix B6. Systematic random sampling means that I have a system to how I'm going to do my random sampling. So I know that I want to randomly select people, but I want to make sure that I represent, I don't have everybody that's going to be all the A's or all the B's as the last name. So I picked every 16th person for an example. And the way that they're doing this, they just take the 85 people that they have, they're looking for 52, they can figure out about every 16th person. Stratified random sampling, a population is first divided into subgroups called strata, and then it's selected from those. So I want to divide everybody into freshman, sophomore, junior, senior, graduate, and then I grab from each one of those randomly. So here you've shown that they've talked about profitability index and split everybody into those categories. And then cluster sampling is divided by clusters using naturally occurring geographic or other boundaries. So I might pick everybody in the BA building or everybody in accounting. It's kind of like dividing them into strata, but it's more of logic from physical rather than some categorical like you're a freshman or sophomore. Non-probability sample inclusion in the sample is based on the judgment of the person selecting the sample. So I'm not using probability where everybody, or probability sample where everybody has an equal chance. I say, okay, I know I need about 5 guys and 6 women. So I look at this and I gauge it myself. I try to do my own type of sampling based on my judgments based on what I need for my study. Sampling error is the difference between the sample statistic and its corresponding population parameter. In other words, when I have a mean, so I do a mean of my sample of the first test, the average person makes an 86. I grab your test, you make a 91. There's a 5-point error in that. Okay. Sampling distribution of the sample mean is the probability distribution consisting of all samples that are possible. Example, TARDIS Industries has 7 production employees considered the population. The hourly earnings are all of these listed. And this is, sometimes you will have a population instead of a sample. And you'll know that because they'll tell you that in the text. They'll say the sample mean is blank. So the formula may be a little bit different. So make sure you're looking for those keywords. It may say the population mean. If my population that I've set up for my study is this class, then I can study everybody in this class. Or I can take a sample of just 10 of you. So it just depends on what I'm looking for. And here's an example of their population. They only have 7 people in their population. There's no point taking a sample at this point. So they want to know what's the population mean, what is the sampling distribution of the sample mean for the sample size 2, what is the mean of the sample distribution, and what observations can be made about the population sampling distribution. Okay, so first thing is calculating the mean. I just add all of them up. I have 7 employees. I divide by 7. Very simple. The sampling distribution of the sample mean, we want to collect all possible samples of 2 without replacement. So we're using that combination formula. I'm looking for, I'm wanting to pair them up. How many different pairs can I have? So I'm looking for 2. There's 7 possible. I'm just plugging this in. And the only thing that has changed is the R is no longer R. It's this little n, which is the sample mean. And then you have the big N, which is the population mean. So the population we're dealing with. We're dealing with a population of 7. We're looking for a sample of 2. How many different combinations could I come up with? I could come up with 21. And again, not replacing, not doubling up. Because they're employees, you can't have Joe right here in the sample twice. So here are all the different combinations. 1 or 2 of the homework problems might ask you to list all the different combinations, and this is what they mean. If you don't do that, that is not going to be detrimental to understanding this, but understand that this is what they're asking for. So on the test, if I ask you, which I wouldn't give you 7 to where it's going to be a large combination, but if I gave you 3 and then I say, show me all the different possible combinations, this is what it would be referring to. And you see that they've taken a sample or mean of each one of these samples that they've done. So here's an example. They've grabbed these 2. They've taken a mean of theirs. This is their mean. Everybody has a different mean depending on whatever their hourly rate was. And then I'm pretty much just taking the mean of all of this data. Sampling distribution of the sample means. Here's an example. I want the sum of all the sample means divided by the total number of samples. So what I've done is I've added up all of the different sample means. These sample means right here. I've added all 21 of these up, and I've divided by 21, and I should come up with the same mean as my answer. When I calculate it the easy way, which is just adding up hourly rates dividing by 7. Central limit theorem, if all samples of a particular size are selected for any population, the sampling distribution of the sample mean is approximately a normal distribution. So it's assuming that most of this information that we're going to be dealing with is going to follow that normal curve, like the one with this standard deviation that we are always doing. So everything's going to follow this. If the population follows a normal probability distribution, the sampling size and distribution will also be normal. We're assuming that if this is my population, then my sample should be reflective the same way. If the population distribution is symmetrical but not normal, the normal shape, it should emerge with small samples. The larger the sample, the more flattened out the curve should get, the more closely related it should be to the population. And the mean of the sampling distribution equal to this mu, and the variance is going to be this sigma squared divided by n. So we'll go through an example. So what you'll be doing here, you can be calculating the z value to be able to make determinations like we did on this graph that we had. And then this is going to play into what we're going to do with chapter 9 and 10. So you can see that this is for sampling, that the formula has changed just a little bit. So you're also, besides dividing by just the standard deviation, it's also divided by the square root of n. So a sample will be a little bit different. And you can see right here, this is going to be for the sample, and this is going to be for the population. They have different symbols, which this formula we're only going to use in Chapter 8. It's going to be a similar formula when we get into the next chapter. So just be able to be aware of that. Quality Assurance Department at Cola Industries maintains records regarding their cola in a jumbo bottle. The actual amount of the cola in each bottle is critical, but it varies, so they want to see if they grab some, what's the sample going to show about the population. They can't overfill it. They don't wish it to be underfilled. Its records indicate that the amount of cola follows a normal probability distribution. The mean amount in each bottle is 31.2 ounces, and the standard deviation is going to be 0.4. So at 8 a.m. they take a sample, and they found out of that sample that it's 31.38. And they want to know, is this so far off that it's still considered normal, or that it's overfilled or underfilled or whatever it may be. So for this one it would be overfilled. Is this an unlikely result? Is this going to be normal, that I would grab one that it would be about this? Is 0.18 unusual? So first you want to find the corresponding z-values. So I want to plug this in. This is where I need my mean and my sample mean that I'm looking for. So here I have 31.38. That's what I grabbed from the one Coke bottle. This is what they said that the mean should be, 31.2. And they gave me the standard deviation already of 0.4, and it was a sample or population of 16. So I plug all of this in and I get 0.18. And that's the z-value. That's going to be what we find on the bottom of that number line. Now we're going to get to where we make decisions based on what z-value we calculate. We'll look on here and say if it gets to this part we make this decision, if it gets to this part we make this decision. But right now you're just talking about the probability. So is this is the probability that it will be somewhere between 31.2 and 31.38 ounces. And this is the probability that it will be overfilled. What can we conclude? It is likely less than 4% chance that we would select a bottle from this normal probability or normal population with a mean greater than this 31.38. So if you look back here, we talked about probabilities. Probabilities, percentages, likelihood that something will happen. Right here in the tails, I get 3.59. So in the explanation, it's not exact. It doesn't say there's a 3.59% chance that you won't get this. It's saying there's about a 4% chance that blank, because you're kind of estimating a little bit. So you have a 4% chance of getting something that's going to be filled over 31.38 ounces. And on the test, I'm going to ask you, not as much on this test, but on 9, 10, and 11 and beyond, excuse me, I'm going to ask you to explain in words, in English. No, don't use the stat terms. Tell me, what does that mean to you as a manager? When I come up with all of this data and now I have this number, what does that mean? Because we can do all these math problems and then we can't apply it to anything. So that's what part of the next test will be about. This is kind of understanding just the calculations. So let's get together in pairs and go through Chapter 8 problems, and then any questions you have for Chapter 7 problems.